Hello everyone, myself Vinay Kumaram. I am pursuing PhD in physics. So in this particular YouTube channel, I'll be teaching physics, chemistry, and mathematics starting from 8th standard till 12th standard. So if you want to learn physics, chemistry, and mathematics, then please do subscribe to my channel. So in my previous videos, I have discussed so many things about Introduction to Euclid's Geometry, which is the fifth chapter of 9th standard mathematics. So I have also discussed about the axioms and postulates given by Euclid, and also introduction for this particular chapter has been done. So now in this particular video, we will look into the example 1 and example 2. Along with that, there is one theorem, that is theorem 5.1, that also we'll look into in this particular video. So now we will look into the example 1 question. So in example 1, they have given a particular straight line. So there is one particular straight line like this. So on this straight line, 3 points are there. One is A, the second one is B, and the third one is C. So these 3 points are there, and you should remember one thing, that this B point is in between A and C. So based on this particular data, you have to prove AB plus BC is equal to AC. So here we have to prove, AB plus BC is equal to AC. And remember, this is one single line, and on this one single line, A, B, C points are there, where A and C are the external points, B is in between the A and C points. So now in this figure, this particular straight line is AC. So here, whatever the straight line I am drawing here is AC. Now I'll draw AB plus BC. How to draw AB plus BC? Draw one particular line and again draw one more line. So this is AB plus BC. So here clearly you can see that AB plus BC is exactly coinciding with AC. So this particular line is AB plus BC. So this is AB plus BC, and this particular line is just AC. So here, according to Euclid's fourth axiom, so according to the fourth axiom, if two objects or if two shapes coincide with each other exactly, then those two are equal. So here AC is coinciding. So here AC is coinciding with AB plus BC. So therefore, according to fourth axiom, therefore AC is equal to AB plus BC. So you can straight away take the fourth axiom and you can tell that AC is coinciding with AB plus BC. Because AB plus BC and AC both are coinciding with each other, AC will be equal to AB plus BC. So this is how you have to prove using Euclid's axioms. Now we look into the example 2 question. So here basically you have to prove one thing, that is you have to prove using any one single line segment you can construct an equilateral triangle. So what do you mean by equilateral triangle? So if you are drawing a particular triangle like this, and in this triangle this is ABC. So here if AB is equal to BC is equal to CA, that means all sides, if they are equal to each other, then that kind of triangle can be known as equilateral triangle. So such kind of triangle can be known as equilateral triangle. So here in this particular example, you have to prove that using any line segment, equilateral triangle can be constructed. So how to construct a particular equilateral triangle using one particular line segment? So first we'll learn how to construct an equilateral triangle using a particular line segment. So in step 1, you have to take one line segment. So this is one line segment. Let's say this is AB. So starting from A till B, there is one line segment. So this line segment we are naming as AB. Using this line segment, you have to construct an equilateral triangle. Now in step 2, take one compass and keep the needle point of compass on A and the pencil what you have attached to the compass that you keep on point B. And from here, from point B, just try to draw one circle making this particular line as the radius of that particular circle. Similarly, do not alter the compass, just keep the needle end of compass on B and keep the pencil on A and draw one more circle like this. So somewhere at this particular point, these two lines or these two curved lines what you have drawn using compass will meet. So this point you can name as C. Now you can just connect this particular A and C, and you can connect this particular B and C. So now here, after connecting this, you can erase this particular curved line which you have drawn. So when you erase that, in step 3, if you remove that curved lines, you will get one triangle like this, which is A, B and C, and here AB will be equal to BC, that will be equal to CA. That means all three sides will be equal to each other. This is how you can draw an equilateral triangle using one particular line segment, that is AB. Now you have to prove that how this is an equilateral triangle. So in order to prove that, now we look into the proof. So here you can clearly see this particular circle. If you just elongate like this and complete this, then this AB acts as the radius. So for this particular circle AB, so here I have just drawn this imaginary line like this. This is one circle, and here also I have drawn imaginary line like this. This is also one more circle. So that means for this particular circle, AB and BC are the radius. So here you can clearly see for this circle, this BC is also radius because B is the center for this particular circle. So since B is center, this AB and BC will be the radius of this particular circle. And for this particular circle, AC and AB are the radius. So that means here we'll call circle 1 and circle 2. So for circle 1, so in circle 1, AB, so this is the circle 1 and this is the circle 2. So in circle 1, A is the center. So this will be the radius of this circle and this will be the radius of the circle. So circle goes like this. So this has become more complicated, but you can refer the textbook image also. So in circle 1, if you consider A as the center point, AB is one radius, AC is another radius. So that means in circle 1, AB is one radius, AC is another radius. So that means here AB and AC are the radius of circle 1. Because AB and AC are radius of circle 1, AB is equal to AC. So now in circle 2, here B is the center point. So for this particular circle what you have drawn here, AB is the radius and BC is the radius because B acts as the center point. So that means here AB is one radius, BC is another radius. So that means AB is equal to BC. So now we have AB is equal to, this is not B, this is C. So AB is equal to AC and we also have AB is equal to BC. So here individually we are getting AB is equal to AC and we are getting AB is equal to BC. So from Euclid's axioms, we can see that one particular thing is equal to the two different things. So here AC is one thing and BC is another thing. And AB is commonly equal to both AC and BC. So that means if AB is also equal to AC and AB is also equal to BC, that means AB is equal to AC, which is equal to BC. So according to Euclid's axioms, AB is equal to AC is equal to BC. So that means this particular triangle is an equilateral triangle. Now we will look into theorem 5.1. So let's look into the statement of theorem 5.1. So two distinct lines can't have more than, so two distinct lines can't have more than one point in common. So more than one point in common. So that means here two distinct lines cannot have more than one point. So how to prove this? Now, in order to prove this, we will take help of axiom 5.1. So in my previous video, I have discussed about axiom 5.1. So in axiom 5.1, we have proved that only one unique line can exist between two distinct points. So let's say there is two distinct points like this. So one is A and other is B. So if these two distinct points are there, only one unique line can be there between these two points. There cannot be other lines. Now, in order to prove this particular theorem, we will initially assume, first we have to assume the opposite way. So let's assume two lines, that is one is LM and other is NO. So this is LM line and the other line is NO line. Now we have to prove that these two lines will not have more than one common point. So initially we will assume that these two lines has two common points. So now we will assume LM and NO. These two lines have two common points. Let's assume, so we are assuming this. So let's assume two lines, these two lines have P and Q as two common points. We'll assume P and Q as two common points for these two lines. So now if P and Q are two common points of these two lines, then according to axiom 5.1, only one unique line, so only one unique line can pass through 2 points. Only one unique line can pass through 2 points. So that means between P and Q, only one line can pass. So only one line can pass. So now P and Q are 2 points and these 2 points can have only one line passing through these 2 points, because between 2 points only one unique line can pass. 2 lines cannot pass, but we assumed that 2 lines have P and Q as common points. So that means this contradicts our assumption. So this contradicts our assumption. So because this is contradicting our assumption, so that means here the theorem is proved. That is, two distinct lines cannot have more than one common point. So that means we are assuming 2 points, but only one line can pass through these 2 points. So that shows here 2 lines cannot pass through these 2 points. So that means here only one common point 2 lines can have. 2 distinct lines can have only one common point. So logically, if you want to understand this, so let's say here L and M line is there and here N and O line is there. So only at one particular point these 2 lines can coincide. So if these 2 lines should coincide at 2 different points, so let's say this is P and let's say there is one more point Q over here. So how do this line coincide with this Q? So if it has to coincide, so now if P and Q are there, then NO should be like something like this. So here if NO is drawn like this, then NO is no more a straight line. It becomes a curved line. So here we are specifically mentioning lines, distinct lines. Lines means it is a straight line. So this is wrong. So you have to draw a straight line. So that means if here L and M is there means, and on this L and M, P is there and Q is there. Two distinct points are there. Here either NO can pass through this point or NO can pass through this P point. So NO can pass through P point or NO can pass through Q point. At a time it cannot pass through P and Q. If it passes, then NO is no more a straight line. So that's why here two distinct lines can have only one common point. More than one common point they can not have. That is what this theorem states, and we have proved that using axiom 5.1. This is all there in this particular video. The exercise questions which are there in this particular chapter I'll be teaching in my next video. Until then, if you want to learn more physics, chemistry and mathematics starting from 8th standard till 12th standard, then you have to subscribe to my channel. Please do subscribe to my channel and stay tuned with my channel. Thank you.